Okay, let us start the lecture. In the previous lecture, we have seen these two theorems, Levy's theorem and Fatou's lemma. Now today we will discuss the Lebesgue-Dominique convergence theorem. Okay. So it's Lebesgue-Dominique convergence theorem. Lebesgue dominated convergence theorem. So dominated means that here the sequence of integrable function is dominated by some integrable function. Okay, let the statement let so let's write here theorem. Okay. Let Fn be a sequence of integrable functions be a sequence of integrable functions okay, and G G is an integrable function G is an integrable function such that mod of Fn is dominated by this G, this are equal to G almost everywhere for all n greater or equal to 1. Now if this sequence Fn, suppose it converges to the sequence Fn converges to, if Fn converges to F almost everywhere, then F is integrable, then F is integrable, and the limit of integral is equal to the integral of the limit function is f here, it's equal to integral of f. अगर आप इसको पूरा भी लिख सकते हो, let's write this is equal to integral of the limit n approaches to infinity fn, that's equal to integral of f. So this is the statement of Lebesgue dominated convergence theorem. So in this theorem we are going to apply the previous theorem, which is Fatou's lemma. So first we will see that this f is integrable. Okay, this f is integrable. F is integrable. Okay, so let us see this first. F is integrable. So since we have this mod of Fn less or equal to G, where G is integrable almost everywhere, this is given, which implies that minus G less or equal to Fn less or equal to G almost everywhere. This is true for each n greater or equal to 1, and it's true for each n greater or equal to 1. So let's apply the limit of Fn is f this gives that minus g lesser equal to f lesser equal to g. So this g, it lies between two integrable functions, and we know that whenever a measurable function lies between two integrable functions, then the function is also integrable. And here f is measurable because it is the limit of sequence of integrable functions, and every integrable function is measurable, so therefore it is the limit of sequence of measurable functions. Since and f is also measurable, and f is also measurable, f measurable भी है और इस कंडीशन को भी, इस इनइक्वालिटी को भी सेटिस्फाई कर रहा है. So therefore this f is integrable. F is integrable. So that's, we have seen that this our function f is integrable. Now let us see this from this inequality. So we have this inequality. We have this minus g lesser equal to fn and lesser equal to g almost everywhere. So from this we conclude that this fn plus g is greater or equal to 0. So let's apply okay, let's apply plus g throughout. So it will be 0 on this side, lesser equal to g plus fn and lesser equal to g plus g, that's 2g. And also by multiplying throughout -1, multiplying throughout by -1 of this inequality, we obtain g greater or equal to, and this g, it's greater or equal to minus fn and greater or equal to minus g almost everywhere. And that is minus g lesser equal to fn lesser equal to g almost everywhere. So which gives the adding throughout g again, so this gives g lesser equal to, it's in minus, okay, g minus fn and lesser equal to 2g almost everywhere. So we have two sequences actually. One is the g plus fn, which is non-negative sequence, and this non-negative sequence is also dominated by integrable function 2g, okay. And second sequence is g minus fn, which is also non-negative, and it's also dominated by the same function 2g, right? So we can now we see that this g plus fn and g minus fn, they both satisfy this Fatou's lemma. They both satisfy the hypothesis of Fatou's lemma. So let's see that. So what's the statement of Fatou's lemma? The statement of Fatou's lemma is the following: if fn is a non-negative sequence of integrable functions such that limit inferior of integral of fn is finite. So limit inferior, that should be finite. The first requirement is that the sequence must be non-negative. So here both the sequences are non-negative, g plus fn and g minus fn, they are both non-negative. So now we check the next second property, that the limit inferior of integral of g plus fn and the limit inferior of integral of g minus fn, so both should be finite, so that we can apply Fatou's lemma. So now let's see that. Now limit how do I do it? Okay, so let's we first see this one, g minus fn, it's integral, okay, because g minus fn is integrable function, g is integrable, fn is integrable, and on this side this 2g is integrable. So this is, And for the second sequence we have integral of g plus fn, it's also less or equal to integral of 2g. Now let's apply. Now let's see the limit inferior, or we can write can see this limit inferior of integral of g minus fn, it's less or equal to the limit inferior of this thing, but this thing is independent of the limit, so it's less or equal to integral of 2g, which is finite, okay. This thing is finite. And limit inferior of integral of g plus fn, it's also less or equal to integral of 2g, which is again finite because 2g is integrable function. So both the sequences, is g minus fn and g plus fn satisfy both sequences, okay, satisfy the hypothesis of what? Fatou's lemma. So let's apply that Fatou's lemma. Now by Fatou's lemma, and you can see that integral, the limit of the integral is equal is what's the statement? What's the statement of Fatou's lemma? It's integral of limit inferior of the sequence is less or equal to the limit inferior of integral of the sequence. So by Fatou's lemma, now by Fatou's lemma, we have integral of limit inferior of the first sequence, that is g minus fn, it's less or equal to the limit inferior of integral of g minus fn, okay, this. And second, integral of limit inferior of g plus fn is less or equal to limit inferior of integral of g plus fn, okay. So this gives okay. And since this sequence fn, it's a convergent sequence, it converges to f, so it's here limit inferior, okay. So it means that limit inferior is same as the limit actually, or you can see it's can do it like this. This implies integral limit inferior of g is as same, it's independent of n, it's g, then minus times limit inferior of fn is equal to, not limit inferior of minus of fn, it's equal to minus times limit superior of fn, that's this integral, okay. It's less or equal to limit inferior of integral of g minus integral of fn, okay. And from second, it's equal to integral of limit inferior of g is g, then plus limit inferior of fn, integral of this thing, it's less or equal to the limit inferior of integral of g plus integral of fn, this implies limit superior of fn is f, because limit of fn is f, so its limit superior and limit inferior both will be same and both are equal to its limit, and its limit is f, so this gives integral of g minus f is less or equal to. So let's apply this limit inferior to this difference separately. So first one is independent of the limit, so it's equal to integral of g, and the second one is its limit inferior of minus times this, that will be minus times limit superior of integral of f. Okay, and from second we have integral of g plus limit inferior of integral of fn is less or equal to the integral of g first plus limit inferior of integral of f. तो यहाँ पर ये इंटीग्रल f है, ओके, और इस ये जो लिमिट है ना ये भी इंटीग्रल है, इट इज इंटीग्रल ऑफ f, तो यहाँ लिमिट इन्फीरियर नहीं लिखना है. So it's integral integral of the limit inferior, limit inferior is equal to f, so it is equal to integral of f here. Sorry, it's here integral of f. Okay, integral of f. Now from first one you can see that integral of g and integral of g, they will go. So then you can multiply throughout by minus 1, as you will see that this gives, or you write this step integral of f is less or equal to minus times integral of limit superior, limit superior of integral of fn, and second is the integral of f is less or equal to limit inferior of integral of f, and that you can see. Let's see this page. Integral of g and integral of g, they will go integral of g here. Okay, so let's see now this. Let's multiplying throughout by minus 1 here. This gives integral of f is greater or equal to limit superior of integral of fn, and integral of f is less or equal to limit inferior of integral of fn. So combining these two inequalities, we get limit superior is less or equal to limit superior is less or equal to integral of f, and integral of f is less or equal to limit inferior. So limit superior of integral of fn is less or equal to integral of f, okay, and that's less or equal to limit inferior of integral of fn. But limit inferior is always less or equal to limit superior है ना, so इसका नाम आप 1 रख दीजिए. Okay, let's name it 1. So here we have seen that limit superior is less or equal to limit inferior, so this gives limit superior is of the integral of fn is less or equal to limit inferior of integral of fn. But the reverse inequality is always limit inferior is always less or equal to limit superior, but limit inferior of integral of fn is always less or equal to limit superior of integral of fn. So this gives limit superior is same as limit superior of integral of fn is same as limit inferior of integral of fn. So that means this limit exists because both are same. This is equal to the limit of integral of fn. Now 1 gives limit of integral of fn is less or equal to integral of f is less or equal to limit of integral of fn. So this gives a limit of integral of fn is equal to integral of f, and that's equal to integral of f. What's f? F is actually the limit of fn as required as. So this proves the theorem completely. So next we will see that if a class of integral function is satisfying certain properties under certain conditions, then not all integral functions, certain integral functions, then all the integral functions will satisfy that property. That we'll see in the next theorem. That's actually it's the definition of integrable function in terms of properties. So we can define integral also in terms of the properties. So integral has certain properties. So the next theorem is let X S mu be a major space. Let X S mu be a major space. And let P be a property. Let this P be a property not possessed by each integral function. Okay, P be a property which may not be possessed by an integrable function. Which may not be possessed by an integrable function. Okay. Now assume that. Let's see these conditions. Okay. Assume that f and g are integrable. Assume that if f and g are now this is our assumption. Okay. If f and g are integrable, suppose they are integrable and satisfying this property. अगर ऐसा है, if f and g are integrable with property p, say, okay, then f plus g and alpha f for each alpha also has it's clear that f plus g is integrable, alpha f is integrable, but here we are discussing about the properties. Suppose f and g are integrable satisfying the property p, अगर ये given है, then f plus g and alpha f for each alpha belongs to R, for each alpha belongs to R also have this property P. ओके आपको ये बात समझ आ रही है? हमने ये हमारी assumption है, अगर f और g integrable है with the property p, then f plus g and alpha f also have that property p. Okay, this is the condition. Second, this is the first property. Now what's the second property? So we are not telling that each integrable function has this property. So there is a if. Okay, if f and g are integrable satisfying this property p, then f plus g and alpha f also have this property p. And second is, if f is an integrable, function, if f is an integrable function, such that for each epsilon positive, f के पास प्रॉपर्टी p नहीं है. Okay, let us see this such that for each epsilon positive there exists an integral function g. There exists an integrable function g with property p. इसके पास प्रॉपर्टी p, f के पास नहीं, with property p. Okay, with एक तो इसके पास ये प्रॉपर्टी p है और सेकंड कंडीशन क्या है इसकी, एंड इंटीग्रल ऑफ mod of f minus g is less than epsilon. ये भी, ये कंडीशन भी इसके पास है. मतलब f गिवन इंटीग्रल फंक्शन है, आपके लिए हर किसी एप्सिलॉन पॉजिटिव के लिए कोई फंक्शन g एक्स हो रही है विच इज इंटीग्रेबल having the property p and satisfying this inequality, then f also satisfies the property p. Then f has the property p. Okay, then f has the property p. Then f has the property p. F has the property. So this is the second condition, and third condition is the following: for each a in S semi-ring, okay, X is mu is a major space, for each set which is in semi-ring A S with its major finite, जिसका major finite है, the characteristic function has this property. Characteristic functions are always integrable. If its major is finite, major तो है ही finite यहाँ पर, तो characteristic function of this set is always integrable. So but it has also the property p. Then the characteristic function has property p. और यहाँ पर इफ नहीं है. ओके, और इसके पास हमेशा ये प्रॉपर्टी p है कैरेक्टरिस्टिक फंक्शन के पास, और बाकी जो प्रॉपर्टीज है उनके लिए कंडीशन है जो कि 1 और 2 में आपके पास गिवन है. अब कंक्लूजन क्या है इस तरह का, देन एवरी इंटीग्रल फंक्शन हैज दिस प्रॉपर्टी. देन एवरी इंटीग्रेबल function has property p. ओके, कैरेक्टरिस्टिक फंक्शन के पास है ये प्रॉपर्टी. ओके, अपनी सेट E. अब इसके बाद हम क्या करेंगे, हम प्रूव करेंगे जो स्टेप फंक्शंस है, जो सम ऑफ कैरेक्टरिस्टिक फंक्शंस है उनके पास भी ये प्रॉपर्टी है, और उनका जो लिमिट होगा उनके पास भी प्रॉपर्टी है. ओके, सो फर्स्ट लेट्स अब कैरेक्टरिस्टिक फंक्शन के पास कब ये प्रॉपर्टी है, व्हेन दिस गाय ऑफ ए हैज दिस प्रॉपर्टी ओनली इफ ए इज द मेंबर ऑफ सेमी-रिंग एस. तो इस पर हम अब इसको हम पहले एक्सटेंड करेंगे, ए को एस के मेंबर्स, ए के जो सबसेट आपने एक्स का लिया ना, जो आपने एस से लिया है, हम इस चीज को पहले एक्सटेंड करेंगे. तो सबसे पहले हम क्या लेंगे, सबसे पहले हम ये लेंगे कि अगर ये ए होगा सिग्मा सेट, इफ इट इज नॉट द मेंबर ऑफ एस बट इट इज द यूनियन ऑफ मेंबर्स ऑफ एस, आई विल सी दैट का ए स्टिल हैव दिस प्रॉपर्टी पी. का ए के पास प्रॉपर्टी है पी ओनली इफ ए इज इन एस. ओके, not for general set E. So first we will see that if A is a sigma set, A is not the member of S but it is a sigma set, it is a disjoint finite disjoint union, countable disjoint union of members of S, then characteristic function of that set A also possesses the property P. Proof. Assume first that A is a sigma set. Assume first that this A is a sigma set. Okay, is a sigma set with its measure finite. Now it's not the member of semi-ring, so here I should write mu star. Okay, which is the outer measure finite. So अगर ये sigma set है, so it can be expressed as a countable disjoint union of members of H such that measure of each set is finite. So there exists a disjoint sequence, there exists a disjoint sequence an of S such that this A is the union an. Now let's put Bn is the union of n sets of these n's. That put Bn is equal to union A k runs from 1 to n. Then what's chi of Bn? Is it possess the property P? Then what's this chi of Bn? Then chi of Bn, this is equal to chi of union A k runs from 1 to n. Okay, and this is equal to what? This is equal to summation chi of A k. So it's a finite sum of these functions chi of A k's, where A k belongs to S, which possess the property P, which possess the property P. Property P by condition by 1 and 3. क्योंकि 3 से आपको क्या मिलेगा? chi a1 के पास भी वो प्रॉपर्टी P है, chi a2 के, because each a k it is in S, so chi a1 has the property P, chi a2, chi a3, so on and so forth, chi n. और प्रॉपर्टी 1 से क्या मिलेगा आपके पास? अगर आपके पास दो इंटीग्रल फंक्शंस है जिनके पास प्रॉपर्टी P होगी, then sum will also have the property P. तो यहाँ पर एक्चुअली सम है ना, sum of integral functions. So by property 1 and 3. So chi of Bn, where Bn is finite digit union of members of S, but we want to prove that chi of A has the property P. Now since this Bn, you can see this Bn, it increases to A, because union of Bn is equal to A, and Bn is increasing sequence, so Bn increases to A, Bn increases to A, Bn increases to A. So if it increases to A, then let's see this. So then so therefore this thing, it means that mu star of Bn also increased to mu star of A. Okay, so you can see this, then integral of mod of this chi A minus chi of Bn, but chi A is greater or equal to chi of Bn because A is bigger than Bn, so we can remove the mod here. This is equal to integral of chi A minus chi Bn. So let's separate the integrals because they are integral functions. So integral of chi is mu star of A minus mu star of Bn. So that approach to 0 as n approach to infinity, because mu star of Bn approaches to mu star of A. So that means for each this limit of this thing is equal to 0. So for each epsilon positive I can find, therefore for all epsilon positive there exists some capital M such that integral of mod of chi of A minus chi of Bn is less than epsilon for all n greater or equal to M. In particular it's true for this M also. So this implies integral of mod of chi of A minus chi of Bm, okay, is less than epsilon. So but chi Bm, it has the property P, chi A is integrable, and this mod of the difference of the integral is less than epsilon. So by property 2, by property 2, by 2, by property 2, by 2 means जो second condition था उसका, by 2 chi A has this property, chi is by 2, okay, yes, by 2 chi A has property P. तो सबसे पहले आपके पास गिवन क्या था, chi के पास प्रॉपर्टी P है, if A is a member of S. अब आपने प्रूव किया if A is a sigma set, then still chi A has this property P. Now next let's take A to be arbitrary measurable subset of finite measure. Now let A be an arbitrary let's take this A to be arbitrary measurable subset, measurable subset of X of finite measure, okay, of finite. तो इससे पहले आपने लिया था सिग्मा सेट इज ऑलवेज अ मेजरेबल सेट ऑफ फाइव, obviously उस सेट का मेजर फाइनाइट होगा because that was given, okay, he is a member of, is a sigma set of finite measure, so every sigma set is measurable. Now let's take A to be any arbitrary measurable subset of X of finite measure, and let epsilon be a positive number. Then there is a sigma set that you have done actually, that's a definition of outer measure actually. Then there exists this the property of the infimum, you can see. Then there exists this a sigma set B is a sigma set, okay, of finite measure, of finite, because measure of A is finite, such that this mu star of B will be less than the infimum, which is mu star of A plus epsilon, okay. यहाँ पर एक प्रॉपर्टी ऑफ इनफिमम, okay, प्रॉपर्टी ऑफ इनफिमम, this mu star of A is the infimum, okay. So this holds this one. So this gives now this B is a sigma set. So chi B satisfying the property P. So this gives integral of mod of this chi A minus chi B. Chi A minus chi B. Okay, let's see this first. So there is sigma set B of finite. This sigma set B has one more property, that it contains A also. That's this sigma set B of finite measure, and A is subset of B. Okay, this is and A is subset of B. Okay, A is subset of B. So what's chi A minus chi B? Since this we have this A is subset of B, so that chi less or equal to chi B, let's write this as mod of chi B minus chi A. Now chi B is greater or equal to chi A, this just chi B minus chi a, both are integrable. We can separate the integrals, and the integral of first one is mu star of b minus integral of second one is mu star of a, and this difference is less than epsilon because chi mu star of b is less than mu star of a plus epsilon. So this difference of this integral is less than epsilon, and chi b possesses the property p, therefore chi a also possesses the property p by 2 chi a has property p because chi b has property p. b is a sigma set के लिए आपने प्रूव किया है. तो अब आपने ये प्रूव किया कि किसी भी मेजरेबल सबसेट के लिए जिसका मेजर फाइनाइट होगा chi a has property p. तो एक्चुअली आपको जनरल इंटीग्रल फंक्शन के लिए प्रूव करना है कि जनरल इंटीग्रल फंक्शन के पास ये प्रॉपर्टी p है. So we are very close now. So from this we conclude that every step function. Now let's now prove it for the step function. Now let phi, which has this standard representation a chi I runs from 1 to n, be a step function. Okay, then each chi ai it's measurable and has measure finite. Then each ai is measurable and mu star of ai is finite. So therefore chi ai has property p. तो हमने अभी प्रूव किया has property p for all I runs from 1 to n. और आपके पास ये जो सेकंड प्रॉपर्टी है, फर्स्ट प्रॉपर्टी स्केलर मल्टीपल प्रिजर्व करता है ये प्रॉपर्टी. सो दिस मीन्स दैट ai chi ai has property p. It's by 1. Okay, by 1 for all I equal to 1 to n. Now again by 1. दस अगर आपके पास कुछ फंक्शन होगी फाइनाइट नंबर ऑफ फंक्शन जो प्रॉपर्टी p को सेटिस्फाई करे, कंडीशन है कि दे शुड बी फर्स्ट इंटीग्रल. ये इंटीग्रल है तो वो जो सम होगा उनका वो भी वो प्रॉपर्टी सेटिस्फाई कर रहा है करेगा. So that means 5, which is the finite sum actually, ai chi ai has property p, has again by 1. तो स्टेप फंक्शन इसको आपने किया प्रूफ. स्टेप फंक्शन इसके पास ये प्रॉपर्टी p है. स्टेप फंक्शन possesses this property p. जनरल इंटीग्रल फंक्शन के लिए कैसे इस प्रॉपर्टी को प्रूव करोगे, दैट्स वेरी इंपॉर्टेंट. नाउ सिंस एवरी इंटीग्रल फंक्शन every upper function satisfying this property, because every upper function is the limit of the sequence of step functions. So now let u be an upper function. Now let f be an upper function. Okay, or u. Okay, let u be an upper function. So then there exists a sequence of step functions phi n such that this phi n it increases to f, and limit of integral of phi n is equal to integral of f. So now let epsilon be any positive number. So choose m such that this mod of integral of phi m minus integral of f will be less than epsilon. So that's the definition of limit से आ जाएगा ये m. Okay. So but this f is increasing. This will be greater or equal to this thing. So it means that or you can say this file increases to f, so let's see this. We have to check the integral, actually integral of phi n minus f. So this means that mod of integral of f minus integral of phi n is less than epsilon, but this is now non-negative because it is actually the increasing limit. Phi n increases to f, so f is actually greater or equal to h phi n. In particular, it is greater or equal to phi m here. Okay. So this means that integral of f minus integral of phi m is less than epsilon, so which implies that integral of f minus phi m. So I replace f minus phi m by mod of f minus phi m, because again it's a non-negative number, so we can replace this by its mod also, is less than epsilon. Now what is this phi m? Phi m is a step function for phi m. Phi m, it belongs to, it has the property p, and f is integral function such that satisfying this property, integral of mod of f minus phi m is less than epsilon. So by property 2, so by 2 जो second condition आपके पास है, so by 2 f also has property p, not f, it's actually u here, so I think should write u here because u is an upper function, so this it's u not f. Okay, it's u, it's not f. Okay, it's u. Okay, so this increases to u almost everywhere, so this thing is equal to u here, and this is u here, this is u minus phi n. So again this is the last step, it's again u here, it's u. Okay, it's not f, it's u. तो अपर फंक्शन u की प्रॉपर्टी क्या है? इसकी प्रॉपर्टी ये है कि इंटीग्रल ऑफ मॉड ऑफ u माइनस phi m इज लेस देन एप्सिलॉन, एंड phi m हैज प्रॉपर्टी p, सो by 2 u has property p, by 2 u has property p. Now let f be any integral function, let f be integrable function. Now let f be integrable function, then f is the difference of two increasing function, upper function, then f is equal to u minus v, where u and v are upper functions, where u and v are upper functions. So by 1, because that property p is closed with respect to sum and scalar multiplication, so by 2 this u minus v has also property p, f has also property p, so property p as required. Every integral function has this property p. So that proves this theorem completely. So next we discuss sub-major spaces. So इसमें भी एक और लेक्चर इसमें आ जाएगा दिस पार्ट, फिर इसके बाद हमें रीमान इंटीग्रेशन डिस्कस करनी है. Yes. Okay, suppose we have a semi ring S, let S be a semi ring, let S be a semi ring. And E be any subset of X. S is also the collection of subsets of X, it's a semi ring. Then this thing, then this one, SE, this collection, it is called E intersection A, where A is member of S. Then this is also a semi ring. then this is then this SE, it's a class of subsets of E, ये E के subsets है, is a semi-ring, is a semi-ring. You can easily verify the properties of semi-ring. Is a semi-ring, and this is called the restriction of the semi-ring S to E, called the restriction of the semi-ring S to E. कि जैसे आपके पास R semi-ring है, अब अगर आप क्लोज्ड इंटरवल 0 1 के semi-ring देखना चाहोगे, so that's the restriction of the semi-ring S over R to its to that closed subinterval 0 1. okay, जैसे R के ना वो सबसे सेमी क्लोज्ड इंटरवल वो semi-ring बना रही है. अब अगर आपको क्लोज्ड इंटरवल 0 1 की semi-ring चाहिए तो आप उसी को रेस्ट्रिक्ट करोगे इस पर. तो you will take interval 0 1 intersection with the members of the semi-ring of R. So that's a restriction of the semi-ring S to R. So now when this mu is measured on this SE, mu तो है ही S पर मेजर, क्या वो SE पर भी मेजर होगा? ये कब ट्रू होगा? ये तभी ट्रू होगा अगर E मेजरेबल होगा. ओके, if E is measurable, then mu star restricted to SE, then mu star restricted to SE, इसको अगर हम SE पर restrict करेंगे, it's a measure, is also a measure, so that is this is a major space. Now this one with the अगर आप यहाँ पर जो सेट है वो E है, इसी के सबसेट्स आप ले रहे हो, that's SE, और मेजर जो ले रहे हो वो आप म्यू स्टार, that's a restriction of mu to SE. This is a major space. It's a major space. So now if E is measurable subset of X, if E is a measurable subset of X, if E is a measurable subset of X, is a measurable subset of X, then a function f from E to R is said to be integral. इसको हम कब कहेंगे इंटीग्रल? सबसेट पर, नॉट ऑन होल X, is said to be integrable on subset. Okay, integrable is said to be integrable over E if f is integrable. The definition is if f is integrable with respect to its major space, if f is integrable with respect to this major space, with respect to this जो इसकी अपनी major space होगी, mu star. So now we can extend the domain of f to whole X. Here the domain of f is E, which is subset of X. The domain of f can be extended to whole space X, by defining, हम वैल्यू क्या लेंगे 0, by defining f x equal to 0 if x is not in E, अगर x E में नहीं होगा, तो अगर x e में होगा वहाँ पर तो फंक्शन ऑलरेडी डिफाइंड है, अगर x e में नहीं होगा उस केस में हम इसका वैल्यू 0 लेंगे। तो इस तरह से सारे x पर डिफाइन होगी ये फंक्शन। सो देन f इज डिफाइंड, then f is an integral function over whole space x, then f is defined, then f is an integrable function over x e पर तो इंटीग्रेबल c है, बाकी पॉइंट्स पर आपने 0 दिया इसका वैल्यू, तो ये f बन गई अब इंटीग्रेबल ओवर होल स्पेस। एंड इन दिस केस integral over x whole space of f, it is 0 outside of e, so you can write this is same as integral over a of f। okay, ये दोनों इंटीग्रल सेम होगी बिकॉज e के बाहर f का वैल्यू 0 है, तो वहां पर तो जो इंटीग्रेशन होगी वो ऑब्वियसली 0 हो जाएगी। So also you can see this also f from x to r is integrable, is also a function f from x to r is said to be integrable, जो आपने पूरे x पर डिफाइन किया ना, e के बाहर आपने इसका वैल्यू 0 दिया, ओवर मेजरेबल सबसेट e of x if the function f into characteristic function of e is integrable over whole space x over x। so this is different over whole space। इसमें obviously आपके पास जो e के बाहर जो वैल्यूज होगी f की वो obviously 0 होगी, क्योंकि अगर x e में नहीं होगा f into का e f x वो 0 होगा, सिर्फ e पर इसके वैल्यूज वो f x की वो f x ही रहेगी। so this should be integrable। and we write this integral of f into characteristic function of e, it's equal to integral over e of f, they are same things। और इसी सेक्शन की अब ये थ्योरम है जो कि इसको हम कल डिस्कस करेंगे इस थ्योरम को।